Hi and welcome back. So in this video we're going to do another ideal gas equation problem, and here's the problem. So we collect 700, and this pen is a bit too thick, I'm going to thin it down. We collect 700 milliliters of gas, but we collect it over water. So we collect 700 milliliters of some gas over water, over H2O. And this gas is going to be at, so it's going to be at 760 millimeters of mercury, and it's also going to be at 25 degrees Celsius. And we want to know what is, so we're collecting this over water, and we're collecting it at 25 degrees Celsius. And what we want to know is what is the volume? What is the volume of this gas going to be, of this same exact gas that we collected over water? What is the volume of this gas going to be if it wasn't over water? If we were able to remove the water molecules from the gas and just have the pure gas that we had collected over water, or the dry gas, what would the volume be? So what would the volume be at standard temperature and pressure, which, by the way, I'll write that down, is going to be 1 atmosphere and 0 degrees Celsius. And one other piece of information, if you're pausing the video to try to figure this out, one other piece of information that you will need to figure this out is that the vapor pressure, so the vapor pressure of water at 25 degrees Celsius, so at 25 degrees Celsius, is 24 millimeters of mercury. Okay, so let's get started on this. And first I'm going to write down our ideal gas equation. We have PV is equal to nRT. And so let's start figuring out what we know. When we know the pressure, right, and we know that this, we know the volume, and we also know the pressure, but we know that this pressure, this 760 millimeters of mercury pressure, this can't all be the gas that we're looking for, right? Because we're collecting it over water. So we're going to have some water pressure in there. And we know that that water pressure is going to be 24 millimeters of mercury. That's how much pressure we are going to be collecting along with our gas. So let's actually, so anyway, we know that. We know the volume, we know the pressure, we know our constant R. We also know our temperature. So what we can do, we can solve for the number of moles. So you can figure that we could say that PV over RT is going to equal the number of moles, and then we can take this number that we solved for, so we can use all of this information along with the vapor pressure of water, and we can solve for the number of moles, and then we can take this N for our number of moles, and we can plug it into another ideal gas equation and solve for the volume. So what would this look like if we solved for volume, but now we knew N, we knew R, we knew T, and we knew the pressure, because our new volume is going to be, our new volume, our new pressure, our new temperature is going to be standard temperature and pressure at 1 atmosphere and 0 degrees Celsius. So we could solve for volume with our new number for the number of moles that we solved for in our first ideal gas equation. And we could say that the volume of our gas, our dry gas that's not over water, that's at standard temperature and pressure, that's going to be equal to N RT divided by P. So anyway, let's get started. Let's get started solving for the number of moles that we have. So let's start plugging in some information. So we have got, let's first start working with our pressure. So our pressure of this gas that we have is going to be, so we've got 760 millimeters of mercury as our pressure, but we know that 24 millimeters of mercury of that pressure is taken up by water, that's how much pressure water molecules occupy in this collection we have. So the pressure of our gas is going to be the difference. It's going to be this number minus 24. So we're going to say 760 minus 24, and we want this in atmospheres, right? So we're going to divide that by 760, and that is going to give us our pressure. Next, we're going to multiply by our volume, which we know is 700 milliliters. So we're going to multiply that by 0.700 for 0.700 liters. And then, I think I'm running out of space a little bit. There we go. So hopefully I'm not blocking that out too much. But now we put in our constant R. So we divide this by 0.08206. And then our temperature. So we have this in Celsius, so we have to convert it to Kelvin. So what's 25? What is 25 plus 273 to get us up to Kelvin? Well, it's going to be 298, right? So that's even a good thing to memorize. You almost on a final exam for chemistry, you almost particularly for 25 degrees centigrade, you probably don't want to always be rushing to the calculator to add 273 to 25 degrees. You might almost want to just memorize that when you see 25 degrees Celsius that it's going to be 298 Kelvin. But anyway, we've figured out, we've gotten everything entered into our first equation. So let's actually solve. So we're going to solve for n right now. And I'll get out my calculator. There we go. Clear. So we've got 760 minus 24. So 760 minus 24 is going to give us 736. So we divide that by 760. And then we multiply that. So multiply by 0.7. And then divide by 0.08206. So divide by 0.08206. And then we divide by 298. And this is what we get for our number of moles. And it's almost like we can say that we don't even need to worry so much about this number because we're just going to use this number to plug into this other equation and ultimately solve for what our new volume would be, right? So I'm actually I'll just leave that on the calculator for right now. And let's say, so this is going to be our sum number n. And remember, we're just taking n, so we're just taking n and we're going to dump it into this equation. So n is equal to r, which actually I'll write out now. It's going to be equal to 0.08206 times our new temperature. And what's our new? Let me scroll over a bit. So what's our new temperature going to be? Well, it's 0 degrees Celsius, so that's going to be 273 Kelvin, right? That's going to be our new temperature. And our new pressure is just going to be 1 atmosphere. So we can just divide all of this by 1, and that'll give us our volume. So let's go ahead and get the calculator again. So this is our number n. What we've figured out so far, that's this number n. So we're going to multiply by 0.08206, and then multiply that by 273, and we're done. We've got our volume in liters. We can actually, let's multiply this by 1,000, so we get it in milliliters. So times 1000, and we've got 621 milliliters of volume. So let's write that down. So this would give us, 621 milliliters of volume. That is how much volume our gas would occupy at standard temperature and pressure that is not over water. So that's how much volume it would be if we're not collecting it over water and we don't have to worry about the vapor pressure of water. So this is what our answer would be. So anyway, hopefully you found this useful. And this actually was there is kind of a shorter way to solve this problem, but it's nice to know that this way of solving it is a bit longer, but on the other hand, it does always work. So anyway, hopefully you found this useful, and I'll see you in a future video.